We present learning guide exploration for efficient sampling-based motion planning in high dimensions. Sampling-based motion planning is used in a variety of robotics applications. However, these planners may struggle to find optimal solutions in high-dimensional spaces due to the size of the search space. Reinforcement learning agents, by contrast, frequently lack convergence guarantees, and their computational cost may prevent us from training them to convergence, but when they converge, they may find near-optimal paths. We present PSST, a variant of stable sparse RT that makes use of a pre-trained but suboptimal reinforcement learning agent. This RL agent is used to bias the search towards promising regions of the state space while retaining all formal guarantees of the SST planner. SST works by uniformly sampling the state space, finding the lowest cost node in a given radius, and then expanding that node with a random action. If the new node is within a radius delta S of an existing node, the node with a higher cost is deactivated. In PSST, we introduce two major changes from SST. First, we perform gradient descent on the sampled actions before doing the nearest neighbor search. And second, we sample actions from a mixture of policies. The convergence of SST and RRT greatly depend on being able to sample the goal state a small fraction of the time. However, for tasks with complicated goal definitions, such as grasping, this may not always be possible. Instead, we sample a random state and perform gradient descent with respect to the time to reach the goal in order to indirectly sample the goal state. We find that sampling a variable number of gradient descent steps allows us to compromise between focusing on the goal and covering the entire search space. Additionally, we sample from a variety of policies, including a random policy to enforce action space coverage, a random state condition policy that attempts to reach the sampled point, and a goal condition policy that attempts to move directly to the goal. We find that while SST tends to have poor path quality as a result of its unfocused search, and pure reinforcement learning agents may have suboptimal solutions resulting from a failure to converge, PSST frequently delivers near-optimal paths and high success rates. This allows our method to excel at solving problems that are challenging for both reinforcement learning and planning, such as the difficult object slang task for the fetch robot. We find that PSST delivers higher success rates than both SST and a pure reinforcement learning agent on a variety of tasks. In conclusion, reinforcement learned policies and value functions can be used to bias planners towards promising regions of state space. Even weak reinforcement learning agents can offer significant benefits in this regard. In the future, we plan to demonstrate this method on real robotic systems in the context of object grasping and manipulation in cloud environments. Thank you.